the trends of quantum computing, challenges of a revolutionary technology for Europe. Quantum computing does not only concern deep epistemic and philosophical foundations of nature, but also revolutionary impact on economy and society. And therefore, the trends of quantum computing in Europe and worldwide are a challenge for our academy, the European Academy of Sciences and Arts, which should be considered in this workshop, bridging foundational research as well as applied engineering and societal impact. We will start with my introduction, and then my colleagues from class 4 of our academy, this is a class of natural sciences, the physicist Marco Robnik from Maribor and Giulio Casati from Como, will take the chairs this morning and this early afternoon with talks from the foundations of quantum computing to the European technology trends. During the coffee break, there is an opportunity to contact Michael Kottusch, editor of the Springer Company, who supported our conference. Now, ladies and gentlemen, it is a pity, but 1 hour ago, we got the message that our Academy member, Anton Zeilinger, has fallen ill, and so he is not available this morning. It is a little bit to me like the Salzburg Festival, when an opera singer suddenly becomes ill, and therefore we will start with the following speakers after Anton Zeilinger. But as announced, let me start with my introduction. This talk is not only in my function as president of the European Academy of Sciences and Arts, but also on foundational research, recently by published books, Quantum Computer in the last year, from the quantum world to artificial intelligence, or in 1900, and in 2019, artificial intelligence, when do machines take the current motivation is, of course, recent introduction of quantum computers. For example, IBM Q system, the first, in some sense, already a universal computer, which can be used for several applications, which was introduced first in 2019, but some days ago, a new version was introduced near to Stuttgart, by the way, with the German Chancellor, Dr. Merkel. You know, she is also a physicist. And on the right picture, you see the Google quantum computer. That was the first quantum computer in 2019 with supremacy with respect to classical supercomputers, but without universal computability. Now, on this background, let's start with some remarks to basics of quantum mechanics, then consequences for quantum computing, some remarks concerning quantum AI, and in the end, future of quantum computing. Basics of quantum mechanics. Of course, a basic is the famous wave particle dualism, which is illustrated here in the double slit experiment. And here it is illustrated in the first picture A quantum system, for example, an electron, is neither a classical body with uniquely predictable location on the screen, nor a classical wave, which is illustrated here in
Wie kan
this
besluiten maken?
with constant interference pattern behind the double slit. If a quantum system, for example, a photon, is considered a classical object, then it seems to pass both slits simultaneously. And that is, of course, very strange and lead to thought experiments like here, the cartoon of the non-classical skier, and we would be puzzled, such as the classical skier here on the right, about the passes of the non-classical skier corresponding to the double slit experiment. So in the quantum world, there is no determined path of a particle like in classical mechanics, for example, here. According to Feynman's path integral, a particle in the quantum world follows all possible paths simultaneously. That means, in short, quantum states are considered probability distributions. A further important property of the quantum world is the superposition of quantum states. And that was nicely illustrated in 1935 by a famous Austrian physicist, Erwin Schrödinger, with his thought experiment of the cat in a box. It is illustrated here. Imagine a cat caught in a box, closed box, together with a quantum system, here a radium preparation, which decays with random, causing a hammer mechanism to destroy a bottle with hydrocyanic acid to kill the cat. As long as we consider the closed box, the whole closed box, as a quantum system, and as long as the box is closed, then that was the argument of Schrödinger, the cat is in both states, dead and alive. When the box is opened, then this procedure corresponds to a measuring process. That means the superposition of both states, dead and alive, collapses, and then the cat is either dead or alive with equal probability. That was discussed, by the way, in this booklet here on the right, which we published in 1990 with the German title, Wie viel Leben hat Schrödingers Katze? How many life has Schrödinger's cat? And I mentioned this book because Anton Zeilinger, he was at that time still in Innsbruck, contributed an article reporting on his first experiments with single photons. Now, you know, randomness, that is horrible for classical physicists like Einstein. And here is the famous quotation, God does not play dice. And in the same year, 1935, he introduced another thought experiment, the so-called Einstein-Podolsky-Rosen experiment, which was later on realized empirically. And following this experiment, we have to imagine a source emitting pairs of photons in opposite direction, and measuring photon 1 here on the left, and following Einstein's assumption of classical realism, the principle of locality, the polarization of photon 2 must be determined before the measurement, because there was no interaction after leaving the source. And that is puzzling for a quantum physicist, because the assumption of Einstein of locality, that means separated photons in distance at different position, this assumption leads to predictions which contradicts, which violates quantum measurements significantly. And therefore, nowadays, it is confirmed that actually, from a quantum physical point of view, two are particles in distance at the different positions are actually in a common state, in a so-called entangled quantum state. Now, what are the consequences of these results in the quantum world for quantum computing? At first, let us consider a classical computer. A classical computer is built up from logical gates. This is a survey of possible logical gates which are connected in circuits, and these logical gates correspond to logical connectives in classical logics with bits 0 and 1, or in logic true and false. Now, superposition, I mentioned it in the first part. Superposition of a quantum system can be realized nowadays by physical quantum systems. For example, here, a photon with alternative polarization states. And here are some other possible physical realizations. I will not go into details. The decisive point is the following. According to classical bits 0 and 1, alternative quantum bits, here illustrated with vertical and horizontal polarized photons, can be considered quantum bits, or in abbreviation qubits 0 and 1, which can generate the mentioned superposition, which is notated here in the usual formalism of quantum mechanics. This means that in a state 0, the quantum system is with a certain probability, and simultaneously in the state 1 with the rest probability. That is a crucial idea of quantum information. Now, what is the advantage of this superposition for quantum computing? An immense acceleration of computational power by computational parallelism. What does that mean? In a classical computer processes information by manipulating bits in gates. That is illustrated here for such a sequence of bits. And then we have an application of the non-gate, which I mentioned before, providing this bit sequence. That means changing the bits in the alternative values. Now, in a quantum computer, a quantum bit before any measurement is, I explained it before, in a superposition state. Here again, this symbolism. And now is the application of a gate operation in this case. It provides a superposition again, and that means with only one application of a gate operation, two manipulations are already realized. And if we generalize this idea now for two qubits, not only one qubit, but two quantum bits, then you can realize it here in this formula. 4 manipulations are already realized by only one gate operation. And if we generalize for n qubits, then we get 2 to n manipulation, generalization of these steps, which are already realized by only one gate operation. That means an acceleration in exponential size, and that means in consequence a gigantic acceleration of a computational power by quantum parallelism. Now, these quantum bits can be illustrated geometrically as state vectors of a unit sphere, a so-called Bloch sphere, which is drawn here, and rotating state vectors here in the sphere correspond quantum mechanically to applied unitary operators in quantum mechanics. And the physicists know unitary operators must be reversible, contrary to classical logical operators. I have not the time here to introduce now all these quantum versions of operators, such as in the classical case. Let me mention only this simple example of the so-called X operator corresponding to the mentioned classical NOT gate, which flips here in the Bloch sphere the state 0 on the z-axis into the state 1. And at least one further operator, the so-called Hadamard operator, because it generates superpositions. This is a Hadamard operator, and you can realize here by simple calculations with matrices applied the operator to the state 0, to the bit 0 or 1, leads to these expressions here of superpositions. So this is an overview of the three-dimensional architecture of a quantum computer with the operators connected in circuits and divided. We have to read this architecture from left to right, divided into layers. And in the first input layer here on the left, the qubits are prepared with up and down arrows corresponding to the alternative bit states. And then you remember the Hadamard operator with the feature to transform the states into superpositions. And that is crucial because superposition, you remember, is the key to apply the advantages of quantum parallelism. And therefore, here in the second layer, the Hadamard gates are applied to generate the superposition. And then in the following layers, all the other special operators are applied, which are necessary to realize a quantum algorithm in such a quantum computer. Now, the final layer here, that is the layer of measurement. And that reminds us of Schrödinger's cat again. You remember when we open the box, that corresponds to the measuring process. And in that case, I explained the superposition collapses into separated possible states with equal chance. And in this case, that means the superposition of all the possible solutions which are calculated in a quantum parallelism by a quantum algorithm now appears with equal chance. So the question, of course, arises, which is the right solution? And therefore, quantum search algorithms for the correct solutions are crucial for quantum computer. The search procedure starts with a superposition of possible solutions for the given input, and they have the same probability amplitude, and then step by step our quantum algorithm, the search algorithm, enlarges the value of probability amplitude for the correct solution and diminish the probability amplitudes for all the other solutions. So for a data set with 2 to n elements and an unknown solution, that means if we try to find the right solution in the brute force way, that is an exponential task. That means in complexity theory of computer scientists, that is an MP problem. And therefore, the search algorithms are necessary. And one of the first search algorithms was the so-called Grover algorithm, which only needs search steps with quadratic reduction. Here, the brute force, here, quadratic reduction, but that still means it is also an NP problem. But nevertheless, it is a reduction. Nowadays, there are much better search algorithms, for example, quantum versions of fast Fourier transformation. But let us consider here the architecture of this Grover algorithm in order to get an idea how they are built up. You remember here the architecture of the quantum computer with the layers, the inputs, and the final layer of the measurement. And that is realized here for the Grover algorithm. Here, the input layer, the Hadamard layer, transforming here the states into the superposition in order to use quantum parallelism, and here the final layer of measurement for the results. And here it is an illustration of this kind of algorithm with the Bloch sphere, which I explained before. You remember changing states are illustrated here by rotating vectors. And the first pointer represents the searched solution, x0, on the y-axis. And the second pointer here points in the direction of the superposition, the uniform superposition after the application of the Hadamard gates. And then in the following process, this pointer is moved step by step according to the apparatus of the Grover algorithm in the direction here of the right solution. Now, let me illustrate another important consequence for quantum computing of famous features of the quantum world. I mentioned the entanglement state, in German verschränkte Zustände. And you remember in the thought experiment of Einstein, he assumed a source with pairs of photons emitted in different directions. And that is technologically nowadays already realized by a satellite as source for pairs of photons, and that means signals and informations. They are sent here to different Earth stations. And the crucial idea was that these particles are in different positions, in distant positions, are in an entangled state. And that means a huge advantage for communication, here quantum communication. The Earth stations here are embedded in networks with connections of glass fibers and quantum repeaters. And that should illustrate the great idea behind this application nowadays, namely the quantum internet in the future to realize quantum communication. Now, in my next part, I like to highlight a little bit consequences for AI, for artificial intelligence. That is my special interest in that field, and we will have later on talks about that. Classical artificial intelligence nowadays means mainly machine learning. And machine learning is here illustrated by neural networks. Perhaps you know these neural networks nowadays are simplified computational models of the human brain. And like in the human brain, here in this simplified diagram, the nodes represent neurons, and the arrows represent the synaptic interactions between the neurons. And the architecture is often divided into layers, by the way, like the neocortex of the human brain. And the main capability of neural networks is the fact that they can be trained by finite sets of data, and then they are able, by learning algorithms, to recognize correlations or patterns in a huge amount of data. And here are different kinds of algorithms, learning algorithms. I will not go here in the details and only highlight one, which is nowadays rather popular, so-called deep learning. Deep only relates to the depth of the neural network here. That means to the number of layers. That is illustrated here in this picture, neural network with 4 layers. A layer is here illustrated by a board divided into squares, and on the first layer only pixels, for example, in a picture can be distinguished by their colors. Then on the second layer, they are connected to edges and corners. And here already partial faces can be recognized, and finally whole faces. But contrary to limited human brains with only 4 and 5 layers, in deep learning, the number of layers in technology nowadays can be improved, can be increased to improve pattern recognition. Now, in order to illustrate a little bit a possible link to quantum computing, let us consider a very simple neural network, the so-called Hopfield system. That is a neural network with only 1 layer. It's a little bit like a cellular automaton or a chessboard, which is illustrated here. And in the squares, there are not only digital states, 0 and 1, or black and white, but there are also superposed states, which are indicated here by the plus. And superposed states, that means that the squares are considered as quantum states, and therefore they are illustrated here by the Bloch spheres, which I explained before, with up and down arrows to indicate 0 and 1, and the rotating arrows to grasp all the possible other quantum states. And these states are colored and illustrated here by the gray color, black and white. And pattern recognition for a Hopfield system, or in general for neural networks, means different phase transitions. The neural network starts with a disturbed pattern, for example, here with the superposition indicating defective pixels, and then step by step in a phase transition, certain prototype here of a letter in very simplified way, the letter C or the letter Y, can be recognized by this neural network with learning algorithms in the classical case. And here the learning algorithms are realized by quantum algorithms, with all the advantages of high-speed computability, parallelism, which I mentioned before. So in the future, quantum computer will process data with quantum parallelism rapidly. Then I also mentioned entangled quantum states, which will open new avenues of distant communication in the quantum internet. And now in the last pictures, quantum neural networks could be transformed into artificial quantum brains with new perspectives of machine learning and artificial intelligence. In the end of my introduction, some remarks concerning future of quantum computing. Nowadays, we are living in a period between the so-called second and third generation of quantum technology. The first generation only means the electronic equipment which we all know since the 80s and the 90s of the last century in everyday life and in factories. Second generation means a quantum computer which can demonstrate supremacy with respect to classical supercomputers, but only for a very special task. And I mentioned in the beginning, that is already realized since 1919, but without the capability of a universal computer. Every laptop nowadays is more or less a realization of a universal computer. Now we have to miss the quantum realization for such a universal computer, and therefore the third generation means the appearance, the construction of such a universal quantum computer. So, and this is my last slide, I think we are on the way towards hybrid computing. That means quantum computing, classical computing, and machine learning are integrated into hybrid computing to accelerate problem solving with increasing complexity in our civilization. It will be not the case that quantum computing will replace classical computing. It will be embedded into an environment of possible computing devices. But especially for Europe, I think we need what is nowadays called standardization and certification of this kind of technology. Standardization and certification in the case of AI, I'm engaged in Germany of a steering group of the government for better standardization of artificial intelligence algorithms in order to guarantee better security and in order to support trustiness in this kind of technology for better acceptance in the public and in industry. In the end, for getting a sustainable and responsible innovation in AI and quantum computing. Now, I thank you for your attention, and let me turn over to my colleague. Marco, please, now you have the chair. Thank you.
Thank you, Klaus. Ladies and gentlemen, as Professor Mainzer already announced, Professor Anton Zeilinger unfortunately fell ill. He's a pioneer and leading expert in modern experimental quantum mechanics, also president of the Austrian Academy of Sciences and member of our academy. So it's a great pity that we do not have him today. But as a consequence of that, we shall move on and start with a lecture by Professor Rainer Blatt from Innsbruck. Let me briefly introduce Professor Blatt. Professor Rainer Blatt is experimental physicist. He was born in 1952. He graduated at the University of Mainz in 1979 and received PhD in 1981. Worked as a research assistant in the team of Günther Werth. In 1982, Blatt received a research grant of the Deutsche Forschungsgemeinschaft to go to the Joint Institute for Laboratory Astrophysics at Boulder, United States, and work with John Hall, Nobel Prize winner 2005, for a year. In 1983, he went on to the Freie Universität Berlin, and in the following year joined the working group of Peter Toschek at the University of Hamburg. Rainer Blatt received the Venia Docendi in experimental physics in 1988. In the period from 1989 until 1994, he worked as a Heisenberg Research Fellow at the University of Hamburg and returned several times to Boulder. In 1994, Blatt was appointed to a chair in physics at the University of Göttingen, and in the following year, he was offered a chair in experimental physics at the University of Innsbruck. From 2000 until 2013, Blatt headed the Institute for Experimental Physics. Since 2003, Blatt has also held the position of scientific director at the Institute for Quantum Optics and Quantum Information of the Austrian Academy of Sciences. He also is a member of the Council of the Lindau Nobel Laureate meetings. In 2018, he co-founded Alpine Quantum Technologies, a quantum computing hardware company. He has carried out trailblazing experiments in the fields of precision spectroscopy, quantum metrology, and quantum information processing. He works with atoms caught in ion traps, which he manipulates using laser beams. In 2004, using the suggested setup, Blatt's working group, at the same time as a team in Boulder, Colorado, succeeded for the first time in transferring the quantum information of one atom in a totally controlled manner onto another atom, teleportation. He has received many international awards and distinctions. He has 38,000 citations and Hirsch Index 91. The title of his talk today is From Quantum Information to Quantum Computer. Professor Blatt, please.
Thank you, Marco, for this extensive introduction, and good morning, everybody. So let me just delve right into the subject. I'm trying to share my screen with you. Okay, that should work now. As the introduction said, I'm going to talk about the transition from quantum information to then the quantum computers. Let me just try to move away. This stuff is really too big on my screen. Okay, here we go. Yes, so what is this about? As we heard already from Professor Mainzer, who introduced many of these things already, we have now quantum computers as one of the big subjects here. Where does it start from? I would briefly like to introduce you again to some of the basic quantum physics things. I was not aware of the fact that Professor Mainzer was doing this already. And then I will start into explaining how we do quantum information processing. First, I would like to address briefly the question, of why do we actually need quantum computers here? Then I would like to give you an idea how we build it via quantum bits, registers, quantum gates, and some realization concepts. And in the end, I would like to give you some ideas how we actually do the quantum way of doing computations. And finally, I would like to show you just a few examples. I'm sure that Frank Wilhelm and Ferdinand Schmidt-Kahler are going to tell you more about this. All this work was carried out over the last 2 decades at the Institute of Quantum Optics and Quantum Information and at the University of Innsbruck in this group, that's the Quantum Optics and Spectroscopy group. And of course, there's a large number of sponsors here who provided the money for this. So let's see what this is about. When we talk about quantum physics, for those who are not so much familiar with this stuff, quanta are individual, that is single elementary packets that come in chunks of matter. That could be atoms, electrons, there's a whole slew of these, or as energy quanta, that's light quanta, that's photons. And the only point that we need to remember here is that quantum physics differs from classical physics essentially in two ways. First of all, a measurement, and I'll show you that in a minute, changes the system. So an observed system is different from a non-observed system, and we have to comply with that, and we have to see how this can be used for quantum information processing. And then one of the key features is that position and velocity cannot be measured simultaneously with zero uncertainty. That is, quantum behave as waves. That is something that was pointed out here by Erwin Schrödinger, and of course the uncertainty relation then cast in the uncertainty relation by Werner Heisenberg. What do we do? In quantum physics, as Klaus Mainzer pointed out so early, we do physics with single quanta, that, for example, single photons. So we study, for example, interaction of light with single atoms, or in particular, the single photons and single atoms. So let's suppose I have a system. My world consists of only these two quanta, that's a photon and an atom. And when we make them interact, then, for example, the following process happens. So the atom gets excited, and my world has changed. I can study now elementary quantum physics. I can understand quantum mechanics and do fundamental measurements. And essentially, what I do now conclude is that before the observation, I had a photon and an atom, so it's two separate quanta. After the observation, I have one atom with an inner excitation that is just one quantum, but at a different energy. So my observation of the photon has changed my world in this case. And that's what we mean when an observation that is a measurement changes the system, but by something that what we call back action. Now, Klaus Mainzer already alluded to that one. The really key experiment to understanding quantum mechanics is this double slit experiment. So we need to understand that quanta behave like waves. What do we mean by that? So consider an experiment where we have, for example, a light source here, which emits single photons. These single photons, as particles, as we often think about it, these single particles are emitted, and they are now going through a double slit, and they hit the screen. And this is an experiment that was made here by the French group Jean-François Roch some time ago. And let me just go away from that laser pointer, and then we can just start. What happens when this is on the CCD camera, the points impinge, then of course a noisy pattern exists, but very soon we see, and I'll speed this up, that wave pattern emanates, as you can see here. So in other words, the pattern, which then builds up in the end collectively by the points that are collected here on the screen, is exhibiting a wavy picture. And in the end, we get a very clear signature of this wavy picture. And interference that leads to this pattern really shows that even though we have single particles to begin with, they exhibit collectively a wave behavior, as was predicted by Erwin Schrödinger. Now, what does that mean? When we now turn over to information processing and physics, and Klaus Mainzer already alluded to that quite a bit, then we think about classical information processing or computing as a physical process, which really means we have an input and we have an output, and in between we have something as that we call information processing. But as Landauer pointed out a long time ago, we have to realize things as physical objects or physical processes, and again as a physical object. So for example, if I take one of my favorite computers here, so that's the abacus, we initialize it to an input state. That's our input, which we, of course, modern language would call it zeros and ones right here. And then we have to move these balls and realizing these algorithms, and finally we read this out. So the computational flow is just going downwards. And of course, current computers process the information according to the laws of classical physics, that's switches, currents, voltages, whatever we have, or it moves on an abacus like this. This is what we call a classical computer. And all of our current computers that we are usually working with, they operate in the same way, whether that's an abacus, whether that's just an accounting machine, or say a full-blown desktop computer. They work pretty much the same way. On the other hand, when we now think about quantum information processing, and then you have to think about the quantum physics that underlies these things. So we process information according to the law of quantum physics. We have to deal with single quanta and the wave-like behavior. And we have to see how we actually can manipulate this. Some of this stuff has already been pointed out by Klaus Mainzer before. Let me just briefly then answer the question, why the heck do we actually want to have quantum computers? There must be some applications in physics and mathematics, so that would be the generic point of view that we have here. And what are these? The entire hype about quantum computers really started around 1994 when Peter Shor from AT&T came up with an algorithm where he could show that if you had a quantum computer, then you could factor numbers with L digits much faster than on a classical computer. And the classical computer, this takes efforts which grow exponentially with the size of the length of the digits here, the size of the number, whereas in a quantum computer, this only grows polynomially. That started the search for the realization of such quantum computers, whether you can actually do it. A little later, Love Grover, and you've heard about the Grover algorithm before, came up with the idea that you could possibly search a database with n entries and you get a speed up which is then going by the square root of the numbers right here, which is not as big as this one, but it's nevertheless a good gain that you could make use of. Something that was pointed out already earlier is something that I'm going to emphasize here. It's a simulation of Schrödinger equations. This is currently a very hot topic because very often it entails solving things that are pretty complicated on a classical computer, as was pointed out by Feynman already in the 80s. And this is currently where most physicists are deeply involved and where we really hope to break even very early, breaking even, meaning that we are really surpassing the computing power of a classical computer. But please bear in mind, there's much more to it than just the computational purposes. As was pointed out in this paper already in the 1996 time by the Wineland group, you could actually use it as for metrology purposes. So for example, in spectroscopy, you can use the quantum computer as an atomic state synthesizer. You can produce states that are tailored for specific measurements and so be much better suited for measurements than the usual equipment that you have. And this is probably something that has been underestimated so far. Everybody talks about a quantum computer, but nobody talks about the quantum metrology, which is probably going to be of much more economic value than initially the quantum computers. And something that we should not forget is, of course, we look into this with a reviewed eye now into quantum physics. So we just review now quantum physics with what I call the information-guided eye notions. And I don't have the time to go into that today, like entropies and things like that are really entering now quantum physics discussions with a really deeper insight. But this is beyond what we are going to talk here. And maybe Frank Willem and Ferdinand are going to talk a little bit about error correction. I don't have the time to go into this, which is also belonging to this area. What do we need for a quantum computer? This was nicely summarized in the late 90s, and here is one particular paper that I pointed out in 2001 by David DiVincenzo. First of all, you need a scalable physical system, which is comprised of well-characterized qubits so that you can form registers to make your calculations. Of course, you want to start, if you want to build a universal computer, so you need the ability to initialize the state of the inputs. You want to start from arbitrary inputs. In order to keep the computation going for a longer time, then you need long relevant coherence times, which are longer than gate operation times. And of course, you need a universal set of gates in order to get these things done. Frank and Ferdinand are going to talk about this later. And finally, in order to read out this result, which of course gives you then a classical readout, that requires a very precise measurement capability, which is specific to the implementations that you have at hand. A little later, David came up with two more criteria. This is first the ability to interconvert stationary and flying qubits. This is what's necessary, the interface function, in order to convert things, say, to a photon, which is then used as a flying qubit and can be used to connect two intermediate, say, quantum computers, or for quantum communication purposes. And of course, you need to be able to transmit the flying qubits in a faithful way between specified locations. This is by now known as the 7 commandments for quantum computing. And according to these criteria, all the hardware that has been developed over the last, say, decades has to be tested. Let me just briefly point out again the elementary building blocks in order to that you see later on when it comes to the real realizations, how this is done. The classical bit we already know. This is what we call our physical object in state 0 or in 1, which is of course our proverbial switch, say pointing up or down. That would be the 1 in this case. And then we form registers as in every computer that we use to display data or to calculate things on our desktop. This is bit rows of zeros and ones. Now the quantum bit is then our old good friend, that's the two-level system, which we denote here in a superposition, and as Klaus Mainz already pointed out, which we usually picture as a Bloch sphere with an arrow pointing somewhere there, and the North Pole and South Pole are the corresponding classical information that we get, the zeros and the ones, the eigenstates of the system. Now the quantum register is then the generalization of these, so we just take several of them. But now comes the difference, because instead of having independent switches side by side, we have to consider now there's a direct product, which is really indicated right here. That is, we have to describe the complete quantum state of the register, which of course in its most general fashion needs to be written down as a superposition. So with all these amplitudes in either notation right here, which really means we get entanglement, as was pointed out in the end, or a superposition of all these states possible. So in other words, here we see the difference. In a classical register, the rest of the register would not care whether you just switch the 0 to the 1 to a 0 and vice versa. But in the quantum register, of course, the quantum state of the entire register changes. And this is what we actually do then, and this is what leads then to the computational parallelism that we have here. So in the computational space that is now built up by the qubits, we get very many computational pathways which are interfering and produce the result. Consider this like say the surface of a lake or whatever, and you have to say two waves that emanate from these points. Of course, you know the coordinates from the points, and then of course you can just do everything here. But in a quantum way, we are just looking at the interference pattern and the non-local behavior. And if you just add, say, more of that, of course, the pattern here changes the same way. So the computational paths interfere and produce the result as an interference pattern. And that, of course, entails that already with very few qubits, you get very many of these computational paths, which you need to control in the end if you really want to do a proper computation. But this entails a mind-boggling result. Why? Because already with, say, 300 qubits, the number of these computational pathways would exceed the number of the atoms in the universe. I have not a good idea what that means. We can talk in the discussion later, what this entails and what it possibly then really means. Okay, but let's come to the next thing. In order to do the operations, we need to run a computer, we need universal gate operations. We already have seen that we need universal, say, single qubit rotations. This would be just turning the Bloch vector to where we want to have it initially, and then we need to also be able to turn it about a definite angle. But we also need these 2 qubit operations, which are analogous to the classical XOR. This is called the CNOT gate operation, and you see here, this is the truth table of a classical Boolean XOR operation, which we now have written down in the bracket notation as is used in quantum mechanics, which already alludes to the fact that it has to hold not only for the probabilities that we get out here, but it needs to hold for all the superpositions. So in other words, when I have a controlling bit which is set to 0, nothing is supposed to happen. But if it's set to 1, then the target bit is supposed to be flipped. But this needs not to hold for the bits itself, but it needs to hold for any arbitrary superposition that I build. And that is the CNOT gate operation, which is really hard to, to do in the first place. But the good news was already found in the mid-90s that together this is already a universal set of gate operations. And once you have that, then you can build a quantum computer. Meaning that we have already a recipe for a quantum information processing. We start with a superposition, in this case, say from 3 qubits. we realize our quantum processor, and in the end, we find another superposition. And the quantum process is realized, according to what I just said, by a sequence of, say, single qubit and 2 qubit operations, where, of course, the phases here are always different depending on the programmer and the algorithm which is underlying there. This is fine, but of course, as Klaus Mainzer already pointed out, this is a unitary operation. Because of these can be broken down mathematically in unitary matrices. You can reverse this completely, so you have not gained any information so far. So in order to gain classical information, you really have to make a measurement. You have to measure this register. And in the case of the qubits, say in our case, it's ions or atoms that we are using, then you see you have to project this, and you get a certain case, in this case, and that comes out in this case. But that depends, of course, on the sequence that you're doing, and you may have to repeat this several times in order to build the probability with which you can actually get that measurement. What are the realization concepts? And over the last, say, 20 years, we have seen many of these, and I don't have the time to go into all the details. Just for those who are interested, there are so-called roadmaps available. The US roadmap is no longer continued, but has still some valuable information based on the Di Vincenzo criteria. And then there's the European roadmap, which is updated. The most recent update is from 2018. But then there's more information if you want to refer to that one, which is released in the, for instance, by the manifesto, when we just introduced the flagship in Europe. And there's a more recent one from the National Academy of Sciences in the United States, which is heavily leaning towards the US-based stuff. So it's not really covering more the European stuff. So I would refer you to all of these at the same time. But talking about this, there's many things that we will hear later. What has been demonstrated first were ion traps, and I'm an ion trapper. I'm going to refer to this in a little bit, but Ferdinand is going to complete this in more detail. Then, of course, you have neutral atoms and traps. There's a whole variety of these things. Neutral atoms in cavity QED, NMR liquids, superconducting qubits are a big subject right now, solid state concepts, and so on. And there's even more exotic ideas. Over the last years, we have, of course, realized that we best use quantum systems that need to be controlled and manipulated at the best you can. And for that reason, mostly these highlighted architectures are currently being pursued, with optical qubits and linear optics quantum computation still in the game for some things. There's also some things used here for mostly for communication purposes, for quantum repeater stuff, but I don't have the time to go into that. Let me just briefly give you a summary what is currently available. There's, of course, IBM. We have seen some of these pictures, the so-called transmon devices. These are artificial atoms, or say like artificial two-level atoms that are used as qubits. And you see the size of these devices. They are really millimeter size, but they have to be embedded in a cryostat and run at very low temperatures in order to get them to the quantum behavior that's needed. And IBM has now, as you've seen, now several 10 qubits available in various places, and they have even the system available on the cloud. Then there's what already was presented, that you've seen the picture before, the Sycamore processor by Google. Klaus Mainzer was referring to as a quantum supremacy experiment. One remark here, because I'm really against the use of the word supremacy. We are not white supremacists, nor are we any racists or something else. And it is always too harsh to say if there's something, a supreme technology. In my way, we should be more humble and simply talk about a quantum advantage. And that's the expression that I have introduced in the European language, and we are really trying to use that instead of supremacy. This is an exaggeration used by the Americans, which I despise. Okay, but anyway, this is a viable processor, and they have shown in the random circuit architecture that they can really do something that is beyond the capacity of a classical processor, although we can discuss why this may not be as spectacular as they already claim. That's a different story that we can discuss later. And then, of course, there's also photonic things here. Things are being produced in Bristol, say in the UK, but also here in Vienna with photonic waveguides for the Walter group. And we have seen a spectacular experiment from the Chinese group from Zhang Weipan, who really came up with very many qubits, and they also showed what they call a quantum advantage. So let me just turn in the last, say, 5 or 10 minutes to what we have been developing in Innsbruck. This is quantum computation with trapped ions, and among them, of course, Ferdinand, who's going to talk more about this later, was one of the leading figures in realizing these gate operations and also the already claimed teleportation experiment. This was all invented, and it was the first realization of a quantum computer ever, at least the concept of it, by Ignace Cirac and Peter Zoller in 1995. This was the starting point of all the hardware. And the idea is to use single ions here in the trap, and I'll show you how this looks like, which can be individually addressed for quantum information manipulation by lasers. And you use an internal structure, details don't really matter here, but you use these single ions as qubits and the address lasers for the gate operations. And the idea was, in order to create the entanglement that we know is necessary to carry this out, we use the common motion of these particles in the trap. Ferdinand is probably going to talk more about this. And after that first initial proposal, we have seen very many other gate ideas that came across and are currently also used, but still the basic idea is still realized today in most of these experiments. And their idea showed for the first time how one can really realize with ions this famous controlled NOT operation, which makes it together with single operations, then a universal quantum computer. And that is really the starting point of all the hardware that was built. How does it work? I don't have the time and I don't want to bore you with this mathematical details, but we just take two level systems in our ions, which are sitting side by side, and then we try to realize this truth table. That truth table really means if I have a control qubit set to 1, for example, this one, I want to flip the state of the target qubit right here. But how the heck should that qubit actually know that there is something in an excited state right here? They are sitting side by side, seemingly independently. And this is mathematically described here by a state vector where you write down the internal degrees of freedom of these ions right here. But these ions are sitting in a shallow trap, which has, say, a harmonic motion. And the basic idea of Cirac and Zoller was to put that harmonic motion in its absolute ground state. So really, they are stock still, they are not moving at all. But again, how should that ion know that there is an excited state? The idea of Cirac and Zoller was to make an operation right here, to rewrite the internal degree of freedom onto, say, 1 quantum of the motion to the center of mass motion here. Then, of course, this starts to move because there's a motion of the single particle, but since they are repelling each other, the entire chain moves. Then I go to the second particle and the second pulse, and I'll make a transition if and only if there was a motion. This can be spectroscopically selected. And finally, I go back and return to the original state. That is, I rewrite this motion quantum back to the internal degree of freedom. So I just restore the controlling qubit. This is how it works, and this requires some very nice individual addressing efficient single qubit operations, small decoherence of the internal and the motional degrees of freedom. And the quantum computer needs to be realized then as a series of these these gate operations or a sequence of these laser pulses. This took about 7 years to realize, and Ferdinand Schmidt-Kahler was with us at that time when we, for the first time, were able to really produce a 2-qubit CNOT gate in Innsbruck. That's it. Things have evolved during that time. In 2013, 2015, we had a much better system. Right now, we are operating now routinely with about 20 to 50 ions sitting side by side. Of course, lasers come in and are used to optically cool the chains. And we also use lasers which come in from the side, according to the Cirac-Zoller idea, with which we can distress individual ions and change their quantum information, which are which are encoded in the internal degrees of freedom. And of course, this is a typical spectrum, really the typical picture that we have in the lab every day, even up to 50. I'll show you longer ones a little later. So when you operate then the system, you really point with the lasers individually there, and then you make measurements, projecting them. So you see a pattern appearing here, and the pattern reveals then maybe an interference pattern that you can read out in the end, which gives you the result of your algorithm. So it's really pulsing with the lasers from the side or from below, whatever, individually addressing or globally addressing the system. And with this, we are able to make now algorithms as a sequence of single qubit and 2-qubit operations. And that is true for any quantum circuit. You can realize these things in the same way with a superconducting quantum computer, which of course is then not done by laser pulses, but by radio frequency pulses. So the gate operations are done by applying the radiation to these individual qubits and make Bloch vector rotations, and thus changing these the quantum state of the entire register. And the analysis usually is done by measuring the system, measuring probabilities. In order to measure now the probabilities for finding superpositions, we have to rotate this Bloch sphere prior to making the measurement, and then we end up with fingerprints that's giving us the probability for finding the system in the excited states, for example, and seeing the coherences. This would be just a fingerprint for one of the build states here with which we analyze things. We call this tomography because rotating, measuring is what you usually call tomography also in the medical imaging. There's other ways to do this in a spectroscopic way, but let's not dwell on this. Let me rather give you a few examples at the end of how these things look like. This is the lab that we use for the one of the quantum computer experiments, and you see a lot of lasers and a lot of optical tables, and this is where the heart of the system is. This is where the ion trap is, where we have our string of ions which are manipulated and controlled by classical computers. And we have implemented all of these algorithms in the past, and we are studying at this time in various experiments just those algorithms which we think can be used to surpass classical computers. This is essentially simulations at this time, as I alluded to in the beginning, fulfilling so the prediction of Richard Feynman in the 80s. Let me just give you an idea of how quantum simulations really are done. Suppose you have a problem to compute, say a difficult spin problem, which you write down as a Hamiltonian, and you know already this is not going to work on a classical computer. Then you can resort to a quantum simulator, which could be, say, an optical lattice, or say a superconducting quantum computer, or say string of ions. Doesn't really matter. Essentially, we have nowadays about 3 ways to do this. The so-called analog quantum simulation, you start with an input state, and then you try to realize your unitary resulting from this Hamiltonian as a sequence, or say application of a certain physical procedure, the application of light or radio frequencies, so that you start the time evolution of the system. This requires a match between engineerable interactions and the model, and after a certain time you stop that interaction and you look what the result is here by measuring the state of that system, how it evolved. And that is quite successful for certain kinds, but it is not really a quantum computer which you can use in a universal way. This is something that is quite helpful and really quite powerful, but not a completely universal machine as you would usually think of a computer. A universal machine requires the breakdown of your algorithm in a sequence of these unitary operations. So you replace this analog evolution by a digital simulation right here, which can be done as a sequence of unitary operations as written down here. It requires very many gate operations, but it has the big advantage that each individual error can be calculated and be corrected for. So it is definitely the way to go for once we are beyond what we call the NISQ area, as was introduced by Klaus Meitzer. In the meantime, we are also using so-called hybrid simulations, where we combine a classical computer with a quantum simulator, for example. So this makes use of the fact that we have a huge Hilbert space available for the quantum states. So we just provide some parameters which tap into the space right here. We do not do the full calculation in the quantum computer end, but we just make an expectation value, feed it back to a classical machine and let it go and find these, for example, in quantum approximate optimization algorithms, then say states of Hamiltonians and whatever of systems as we have it here. Just a few examples without going to the details. When we have a register like that and we are studying, for example, the magnetization of an atom, so we invert one atom right here and then let it go and see the time goes down here, then we see that this magnetization spreads, for example, under the interaction of a Ising type Hamiltonian in this case, in such a way that we see that the magnetization, or actually in this case entanglement, propagates and in the quantum register. So we can really see how the interference patterns really apply and how this really spreads in the system. We can also do chemical calculations. So quantum computing of chemical potentials is one of the big systems right here. This was done on the superconducting quantum computer by this is H2, the H2 molecule by IBM. And we looked into this a few years ago in more detail. We just looked here, this chemical precision. And you see, indeed, say our quantum computer in Innsbruck is able to do this even finer here because we concentrated on things and our machine has less errors than here. The global picture is nicely met by the IBM machine, but in Innsbruck we were able to do this chemical precision. This is a hybrid quantum computer. Again, we can study molecular reactions. We can look for basic algorithms, as I mentioned, the quantum approximate optimization algorithms, and it could also be the basis for quantum machine learning, as was alluded to by Klaus Mainzer already. Now, let me just summarize things here. We have an analog quantum simulator with trapped ions here for non-equilibrium dynamics, many body quantum systems. We have universal quantum simulations where we already apply several hundred gate operations in a digital quantum computer. We can actually attack already hard problems by going to lattice gate theories and quantum chemistry, as you've seen. And the largest entangled quantum register today is definitely one with 24 entangled ions. And we are working every day to realize even bigger quantum registers which are entangled, which is my big criticism, for example, with the superconducting quantum computers. They show at most 9, 10, 12, in the IBM case, even up to 18 or 20 entangled particles, but they just conclude this in an unfair way because they just call what they call error mitigation and things like that, whereas we really produce GIC states, Greenberger-Horn-Zeilinger states, and really know that there is definitely entanglement in the system and shows the powerful behavior of these registers. Then we have also demonstrated the scalable Shor algorithm, which can be run on our quantum computers. And we are pursuing quantum metrology for improved frequency standards in quantum logic spectroscopy. That's it. Let me just conclude with my dream. What we are currently working on is, of course, that's already the next generation. We want to go to local logical qubits. Ferdinand is going to talk more about this later, which are protected then by error correction and finally interconnected via either dipole-dipole interactions on a chip like this, or with ion cavity interfaces for a network. And then, of course, the idea is to use then these long strings. We have already strings with up to 120 ions, which we are currently using, but this is a typical one that's 50, 60 ions that we currently use for simulations. We need better fidelities, better gate operations, a lot of these things more. And then eventually, the holy grail of the entire thing is to eventually keep the qubit alive with error correction. This is something which is what I call the biggest challenge at this time, and this is what we need to really go on. The NISQ scale architecture is being pursued right now also in the big German programs and worldwide, but we already have to think ahead for the next step. And then everything else right here, which is listed here, the really interesting things for industry, for applications, for physicists alike, that will be a lot easier once we have mastered that. That's it. Let me just say this is a large team that is in Innsbruck available doing this. Of course, this would not work without strong collaboration with theorists, of course, in particular with Peter Zoller, but many others here, and Joe Emerson and Miguel Angel Delgado in Madrid, and many others. Finally, the names don't really matter. Let me just show you where we are. This is where the quantum computer in Innsbruck is located, right next to the airport. And as was already mentioned, we have now a company, Alpine Quantum Technologies, that is able to produce these quantum computers. And by the end of the year, really by the end of 2021, you can buy quantum computers already in these two cabinets, which were two 19-inch racks. And this is the inside of these 19-inch racks. And what you see here down there, that's our quantum engine. That's really is only slightly bigger than a shoebox. Everything else is lasers and electronics. And this is the quantum CPU as it is right now. And if you really want to have one, please contact AQT. Thomas Mons would be eager to sell you one or to get you access to this machine, which is now readily available already on the cloud. With this, thank you very much for listening and for your attention.
Thank you.
Thank you very much, Professor Blatt, for this excellent presentation. We have now time for questions and comments, please. Professor Mainzer.
Yeah, only one short remark. In my talk, as well as in your talk, we did not highlight the great decoherence problems which are typical for the quantum world. And especially now for quantum computing, perhaps you can underline or explain a little bit more the problems with decoherence in quantum computing.
Thank you. That's a good point, and also it's an intricate point. That's why I did not mention it, because we can discuss for hours on that. Decoherence, for those who are not so familiar with that, is simply the fact that we lose the contrast in, say, the superpositions when a system like a qubit is coupled, say, to the environment. This is even more important when we have, say, an entangled register, where the superposition is carried out, say, across an entire register. And then, of course, the more degrees of freedom you have, and the higher likely is the chance that they couple to, say, thermal degrees of freedom, say, other things like this. That is really the problem for a quantum computer. So we have to use states as two qubit, as the two-level systems that are intrinsically stable. For this reason, in atoms, we use states that have no spontaneous decay, at least in the time when we talk about these manipulations. In superconducting qubits, you have to make sure that these things have very low temperatures, so that things are not influenced by the say the radiation and the temperature of the environment there. And
thank you very much. Okay, let me share my screen. Okay, so do you see my screen? Is everything fine?
Yes. Yes.
Good, very good. So thank you for the invitation. Thank you for this nice introduction. Maybe just as a point, I joined recently also the Schaffhausen Institute of Technology. So that's my second affiliation. On this first slide, so you see some quantum experiments. Actually, quantum cryptography with single photons traveling between Geneva and Lausanne in an optical fiber cable below Lake Geneva. I think what is interesting and nice here is that at the same time you see a quantum experiment, and this is a satellite photo. And of course, that is a contrast between satellite picture, big scale, and quantum, which is supposed to be on a small scale. So let's start. So the title is From Quantum Foundations to Applications and Back. So let's start from the foundations, going back to an experiment which is very famous in quantum physics, done in Paris by Alain Aspect and his group in 1982. All what you have to remember, it was a lab full of stuff, big laser, here you had a atomic fountain and so on. And at that time, that was just considered as a curiosity lab. People didn't really take it seriously. That was not and very far from mainstream physics. Now, it is already interesting, and let me start with this introduction to quantum non-locality, which has already been alluded to this morning. So let's suppose you start with two photons, two particles, let's say photons, a blue one and a red one. And so they're distinguishable. So you can say that the blue one, let's say to the left, to Alice, as we say, and the red one to the right, to Bob. And the joint state of these two photons is written in this form, which is not a product. It is a superposition of two products. So this is one of his famous entangled states. Now, what can Alice do on her side? She can analyze these photons, polarization, or with interferometers, never mind. And she can tune her measurement. You know, she can rotate this polarization analyzer or maybe change the phase in some interferometer. And what she's going to observe on these detectors, single photon detectors here, is nothing interesting. It's just completely independent, maybe a bit of noise, but essentially it's completely flat and independent of the measurement setting. And it's the same on the other side, on Bob's side, who now has his measurement setting B. And again, the single counts is totally flat, uninteresting, just noise. However, because we have two particles here, we can, of course, now combine the two outcomes, send that to some coincidence electronics. And now in the coincidence counts, we'll see interference fringes, sinuses, that depend both on A and B. They depend on the difference or the sum, depending how you define that. So we see a structure in the coincidence while we have nothing on the individuals. And now, if the statistics of this correlation that we observe cannot be described by local variables, or just something happening here and something happening there, then we talk of quantum non-locality. And this is fascinating, and that's going back to the 80s or even to Bell inequalities in the late 60s. So Aspect experiment was in the early 80s, and 15 years later, you see that in this box, we have actually been able to pack the entire lab that you had in this Aspect experiment. Now everything is in a little box. I'm not going to describe everything, but you see this enormous technological change in 15 years. And now the photons are really coupled into these optical fibers here, which are really just telecom fibers, and you can connect them with standard optical connectors. And you can put, let's say, the source here more or less in the center of Geneva, and have Alice a bit north of Geneva in a town called Bellevue, and Bob south of Geneva in another town called Bernay, with about a bit more than 10 kilometers in straight line. And so I call that the real world lab. And indeed, we can get these two photon interferences, these coincidences here. And you see that indeed you get these coincidences that oscillate in function of the two measurement settings in Bellevue and in Bernay. And okay, the visibility is not 100%, it's 95% more or less, which is high enough to demonstrate this non-locality or this entanglement phenomenon. So we get a violation of something called the Bell inequality over more than 10 kilometers. And we conclude, and I think at that time, that was the conclusion. Physics is beautiful. And that's nice. And it is intellectually fascinating. And one asks ourselves, how does nature do it? But the real revolution in quantum information science is not to be satisfied with these kind of questions and answers. There is a second aspect. What can one do with these entirely new sorts of correlations? After all, if you find something which is completely new, whether it is in physics, in biology, whatever, if it is completely new, it should open new possible applications. And that took some time until someone, actually a young physicist at that time, came with a beautiful idea. He noticed that after Eckert, I'll come back to him, he noticed that actually non-local quantum correlations is nothing but cryptographic keys. You know, you can say these are sequences of 0 and 1s whose security is guaranteed, I'll explain that in a while, by the fact that they violate Bell inequality, that they show non-locality. So let's see that. So here is the paper by Arthur Eckert in the early 90s. So you have Alice in her lab. Let's say this is the basement of one bank. This is the basement of another bank, whatever, hospitals, whatever you want. And at some point, of course, they exchange some photons. And then they close the door. And only at this point, they decide which measurement they are going to perform. And they need at least a binary choice. Let's make it binary. And then we observe, of course, some outcomes. That's on Alice's side and similar on the other side here. And now we can publicly announce just a fair sample, a few % of all the data. And with this, we can see whether this conditional probability distribution of getting results A, B, assuming we have made the measurement X, Y, whether this violates some Bell inequality, whether this shows some non-locality. And really this Arthur Eckert's insight was the following. If that violates some Bell inequality, then necessarily this correlation contains secrecy, irrespective of any details of the implementation. Why is that? The intuition is that if it violates some Bell inequality, then there are no local variables. But if there are no local variables, there cannot be an adversary that holds a copy of these variables. You know, you cannot hold a copy of non-existing variables. That was the intuition of Arthur Eckert. Admittedly, until it was really rigorously proven, it took almost 2 decades. You see here some papers, some references. But the intuition is pretty clear and beautiful. And then you can go, and if you have good students and students with some entrepreneurship mind, you have a spin-off from the university that was 20 years ago, actually 2001. And okay, that was the first kind of cryptographic box here. So that's Alice or Bob, they look the same. On top, you have the encryptor and the decryptor, because this is only producing cryptographic keys or passwords, if you like. And then you put one in Geneva. And this is, for instance, today used by some banks in Geneva with backup systems in Lausanne. Now, these boxes today, they already look smaller. Actually, the last version is even half that size. And you see, the source is no longer in the middle. We put the source on one side, on Alice's side, let's say, it doesn't really matter. And so what is coming out of this is only one of the 2 photons that goes to the other side. And so at the end, you just have kind of telecom boxes that now produce cryptographic keys whose security are guaranteed by the laws of quantum physics. And if you open these boxes, you find a lot of electronics inside. I'm not going to tell too much about it. You find also a bit of optics, of course, laser, intensity modulators, attenuators, and the same or similar on the other side. What is really different from a standard telecom box is that at the end of the optical line, you have these single photon detectors here. And so really the difference is that with a standard telecom box is that these quantum key distribution engines are like telecom boxes, except for this single photon detector. That is really the difference. And today these are very standard and reliable boxes. So the company IDQ was established in 2001. It has today more than 100 employees between Geneva, South Korea, Boston, and it has 2 divisions. One is quantum safe security, so mostly quantum cryptography, but also some quantum sensing. And I want now to tell you a bit more about these 2. And I have already said about quantum cryptography, but another thing which is very important in security is just randomness. And to produce randomness, in principle, on paper, it's very simple. You just have a single photon source. You have put a beam splitter, 2 single photon detectors. One you label 0, the other one you label 1. And then what comes out is actually random. So this is super nice. You can put it in little boxes, kind of matchbox here. And it gets certified by many entities here and there. Now you may ask, how is it that we the quantum physicists, we really trust that this is random, that there is not something going on behind the scene here? And to really check that we have quantum randomness, we have to go back again to non-locality. And we make some assumptions. First of all, we assume that distances really exist. You remember these 2 villages, Bellevue and Bernay, they're really at a distance. And secondly, we also assume that there is no superdeterminism conspiracy, so that they exist independent systems. In this way, we can put our random number generator at a distance, and we can use some independent measurement settings here to choose what to measure exactly, to rotate some polarizer, for instance, both on Alice and on Bob's side. And then we need, of course, to violate some Bell inequality. So this is one form of writing a Bell inequality. So we can violate Bell inequality, so we demonstrate non-locality. And then there is a theorem. This is just a mathematical theorem. There's no way to go around that. And the theorem says that assuming these two assumptions, very, very general, assuming this fact, so this is not really an assumption, it's a fact, an experimental fact, then you have that actually the outputs here on both sides, on Alice and on Bob's side, are truly random. This is something which today is well understood. Okay, now you have that beautiful concept. You can put it into these kind of boxes, and then you go to the engineers. And engineers are really fascinating persons with ability which goes actually beyond physics, I would admit. And so they have been able to put now all that into this little chip. This is really a millimeter-sized chip with also a super low consumption, as written here. And now this little thing you can put into a smartphone. So here, as you see, this is a smartphone from Samsung. So now people who have this kind of smartphone, as myself, for instance, you have a quantum device, a quantum random number generator in your pocket. This is the first application, mass application of quantum technology at the single photon or a single quanta level. Okay, today I have to admit, you can buy that in Korea from this South Korea telecom company, or you can also buy it from in Vietnam from the WinSmart here. And why all that is in Asia and not in Europe or not in the US also is a good question. Now I want to give you another example of some application, this time in quantum sensing. And so here will be an application of superconducting single photon detectors to rockets. This is the European launcher. Actually, it's Ariane 6, so this is the next one, which has not yet flew, but which will be the first launcher, space launcher, which uses optopyrotechnic to trigger the motors. So instead of having conventional electric pulses like that, it will be optical pulses. And the idea is you send this optical pulse, let's say, to one of these motors. And by some pyrotechnic, this is going to trigger on the motor. And of course, you have to make sure that these optical pulses will be guided by optical fibers, and they should reach all these motors in the appropriate time order with the appropriate timing. And for sure, the optical fiber should not be broken and all that. So the main idea here is, one of the challenge here is to test all these optical fibers. And the standard way to test optical fibers is with a technique called optical time domain reflectometer. You send a pulse down the fiber, and you look at everything that is back reflected, light that is back reflected. The problem, if you do that here, by just sending your pulse, you trigger on the motor. So you cannot do that. And the answer is, let's go to super low intensity. And super low intensity, light intensity means you need single photon detectors. And more precisely here, we really developed at the university with my colleague, Professor Hugo Sbinden, single photon detectors using, again, superconductivity. So it's not the same as these superconducting qubits we mentioned this morning, but it is also this phenomenon of superconductivity that allows one to really have more than 90% detection efficiency. This is huge for photons. To have some photon number resolution, you can count photons. Actually, on this here, you say 4, but you can even go a bit higher today. And very importantly for this application, to have a very low time jitter. So you can be very precise here. And so this is a bit of a sketch. So you have actually, let's say, your rocket here, and all the control is a few kilometers away. And you have many connections and all that kind of stuff. And you have a resolution that goes down to a centimeter. Okay, so this is a nice and maybe somewhat surprising application of a component which is useful for quantum information. Of course, this is not directly quantum information, but I think it's nice to see applications that go beyond, let's say, the core of quantum information. Now let me go, so that was going from foundations, quantum non-locality, quantum cryptography, quantum random number generator, this surprising application for this space rocket. Now let's go back from these applications and go back to foundations. So what will be the next step now for quantum cryptography? Quantum cryptography, you can go and buy it and it works. That's okay. You have it in many places around the world. But there is a distance limitation. You cannot go much beyond, let's say, 100 kilometers, maybe 200 kilometers, like that. Okay, records are a bit further, but you cannot go over continental scale. You cannot go from Rome to Helsinki, let's say. That's impossible. So what you need is a network, a complete network, where you would have between Alice and Bob some source, or maybe you put the source in Alice side, in Alice box, and then between Bob and Charlie, you'll have another source, independent source here. And what you can do here in the middle is some joint measurement, like the one that also the people in quantum computing use, the Bell state measurement, as we say, which is going to entangle now Alice and Charlie. And you can have a complicated network as sketched here. And now you can emphasize that here we are going to have independent sources. Maybe this source and that source are 50 kilometers away. They're really independent. I know you have this entanglement here, you have the entanglement there, you do this Bell state measurement in the middle, and this is really quantum teleportation. So you're going to teleport this qubit or this photon, the state of this photon, to the right-hand side here. And so you have now entanglement over twice the distance. So this is really the idea of a quantum repeater. You can go further and further and further. Of course, you can repeat that. But see, it is also fascinating from a fundamental point of view, because now we have entanglement between photons that have never seen each other. They have never interacted. Okay, now one thing which is here still a bit hidden is that these two photons here in the middle, they have to be measured simultaneously, which means they have to be there at the same time. At the same time means you need synchronization. How do you synchronize a network, whether it is a classical or a quantum? You need memories. And if it is a quantum, you need a quantum memory. So you must have that your photon here, including all its quantum properties, should be mapped into a memory. And in our case, the memories are actually optical crystals, transparent crystals that that contain billions of rare earth ions. So these ions, they sit in this crystal, they don't sit in vacuum, they sit in the crystal, but they're kind of frozen in the crystal, and the crystal is put, you see it here, in a cryostar at some 3 Kelvin more or less. And so interestingly, here you have that this quantum state of the photon is now coded in a huge entangled state of actually billions of atoms. I'll come back to that. And on demand, with a laser pulse, for instance, the photon should come out, keeping all its quantum properties, including possibly the entanglement with some other photon. So how do you do that? So absorbing a photon here, that is very simple. Of course, you can also stop a photon with your hand, but you want to do it in a reversible way. If you just do it like that, you know, the photon will, after some time by spontaneous emission, be irradiated at a random time in a random direction. So your photon is lost. But what you can do is to shape the absorption spectrum by some optical pumping. And by doing this shaping here, you now have that after 1 over delta, where delta is in frequency the distance between two of these frequency comb teeth, you'll get a rephasing. And because of interferences, you'll get that the re-emitted photon will really go in the forward direction. So you know when it comes out, and you know in which direction the photon comes out, so you can catch it again in an optical fiber. And so here we have some example where again we look at coincidences. We again have these sinusoidal coincidence counts, and indeed we can again violate some quantum inequalities. So again have some quantum, some non-local quantumness, and also randomness. Okay, very nice. And here is a case where we had actually 2 of these crystals, okay, just a centimeter apart, but it wouldn't be very difficult to put kilometers between them. Just so you see it, they look like that. They're about 1 centimeter long and a few millimeters in the other directions. Now you may ask, is that now a Schrödinger cat that was mentioned this morning, or just is that kind of macroscopic entanglement? Same question we heard this morning also. And here the answer in this experiment published here is that there is a way to guarantee, to certify from the experimental data, the raw data, that at least 16 million ions are entangled. So that's a huge number, no? 16 million. I'm actually sure there are many more, but from the data, there's a bit of noise, so we come to these 16 million. Now, I should also immediately add to that, that this is really, again, fascinating. We are back to the foundations, but this is not a useful entanglement for quantum computing. So this is why no one this morning mentioned this kind of thing. However, it is a useful entanglement for quantum memories, because it's really this large entanglement that guarantees or maximizes the chances that the photon comes out in the right direction. Okay, so we come back to now this conceptual quantum network with these independent sources of entangled photons. And we come back to this idea, how are we sure that this is really secure, that this is really quantum and not just a fake quantum? So we're going to compare the statistics we get here with the case where we had actually local variables. Here and everywhere, all the sources would now no longer produce entanglement, but just produce independent from each other local variables. So this variable is independent from that one, independent from that one, and so on. And so we can again ask, can I simulate my quantum statistics? If yes, I have a local model, there's no security. If no, then there is some quantumness in my network. Okay, maybe I jump over that. And here I getting close to the end. So let's suppose now, to make it simple, we just have A, B, C. And you see between A and B, you have one source. Between B and C, you have one source. Between C and A, you have one source. And you have that each only produces a result, no measurement setting. So everyone, Alice, Bob, and Charlie, they always perform the same measurement. So you have somehow a little 6-qubit, because every source is 2 qubits. So 6-qubit toy universe without inputs, without measurement settings. And we want to prove quantumness. And we want to prove that the outputs here contain some randomness. And indeed, very recently, you have a lot of results coming out here. I still a lot of questions, open questions. This is really, I think, fascinating fundamental physics. Maybe if someone is interested here, you have a 2-month-old review paper by these people. 2 of them are my former students. And so we are here really back to the foundations. And I think it's a perfect and a nice illustration that we started from non-locality, aspect experiment, Arthur Eckert's insight that actually non-locality means a cryptographic key. You can produce these devices. You can industrialize, commercialize it. Same for random number generator, even in smartphones. You have other application of single photon detectors. But at the end, when you see what is coming next, these quantum networks, these again open entirely new fundamental questions. So at the end, the vision here is really that the theory of electromagnetism was invented in the 19th century. And all the associated technology completely dominated the 20th century. And likewise, quantum theory was developed in the 20th century, and quantum technology is going to play an important role in our 21st century. So historically, between classical and quantum, there was mostly a tension, all these paradoxes and so on. But now all that is going to join into a common hybrid, as Rainer Blatt said this morning, technology that is going to take the best of both worlds and produce 21st century technology for the benefit of society and of human knowledge. So thank you very much for your attention. Thank you for all those who came on time to this early talk of the afternoon. Thank you.
Okay, thank you to you, Professor Zheng. It was very interesting talk. So there is any question? Okay, Klaus?
Yeah. Yeah, thank you for your very exciting talk, I must say. I have a lot of questions, but I only want to highlight or underline a remark in the beginning of your talk concerning randomness, that nowadays it is possible to have something like an app for randomness, not only in the usual sense, classical sense of dice, but in a mathematical sense, in the sense of quantum theory. But then I have a question. It was very interesting in the context of your explanation concerning the quantum internet, your remarks on macroscopic entanglement, you said. So my question is going a little bit further. I remember when I was professor in Constance, I cooperated with colleagues of quantum chemistry at the ETH Zurich. And they were interested in entanglement, not only in the microscopic world we discussed until now, but in, of course, the molecular world, the meso world, perhaps up to cells. What is your opinion concerning macroscopic entanglement?
Yeah, thank you for all your remarks and the question. So I think this is, okay, it's a talk in itself. So macroscopic entanglement, I put a question mark here. So I'm not claiming that this is a macroscopic entanglement. Actually, if you go and read the paper, I'm claiming this is not macroscopic entanglement. However, it is undoubtedly entanglement between two macroscopic objects. But we don't entangle all the degrees of freedom of these macroscopic objects. Actually, we only entangle 1 degree of freedom of each of these two crystals. So the green one and the red one, illuminated by lasers here. And each of these single degree of freedom is actually a collective excitation. It's called sometimes a spin wave. It's a collective excitations of billions of ions in this crystal and billion of ions in this crystal. So because we only have 1 degree of freedom, even if it is a involved degree of freedom, I would not claim that this is macroscopic entanglement. But maybe the most interesting answer to your question is that today there are many ways of starting to understand what macroscopic entanglement means. You know, Schrödinger with his cat, he had some simple ideas. Well, simple is maybe not the right word, but you know, some ideas that were so far away from any possible experiments that there was no real good way to analyze all the subtleties in these kind of experiments. Today, we can count things. We can see how many electrons this morning in this qubit flux qubit contribute here, how many ions contribute, but how many degrees of freedom is that? What is really the complexity between all that? And I think macroscopic entanglement is not a single concept. It's a variety of concepts with many facets and fascinating facets.
Okay, thank you.
Yeah, thank you. Some other question? No, so okay, so we can move. So thank you, Professor Jizeng. It was really
thank you.
Thank you. So we can move to the next speaker. Yes. Okay, we can move to the next speaker, Christian Bauckhage, who is a professor of computer science. More specifically, is professor of intelligent learning systems at the University of Bonn, and is also the lead scientist for machine learning at the Fraunhofer Institute. He obtained a PhD in computer science from Bielefeld University, and he has a long experience as a data scientist, not only in academia, but also in industry. And he is expert both on theory and practice of machine learning and artificial intelligence. There is one thing that I would like to mention is that Christian is a frequent public speaker and is a passionate proponent of open science. So in my opinion, this is an important point, since in the future society, it will be important, I believe, that the largest possible fraction of the general public will be able to understand the meaning of scientific discoveries. I think this is a central point. As we know, machine learning is a key technology in relation to cognitive system and artificial intelligence. And indeed, an increasing number of different sectors are currently undergoing a substantial transformation because of machine learning and artificial intelligence-based technology. And this includes manufacturing, logistics, medicine, up to relevant questions about the impact intelligent machine might even have on our daily lives. So a very recent research topic, which is becoming popular very rapidly, it seems to me, is quantum machine learning, which is the subject of today's talk by Professor Baukach. So please.
Thank you very much, Professor Casati, for this nice introduction, and thanks for having me at this really exciting workshop. As it was mentioned, I am a humble computer scientist, and the presentation I'm going to give is a bit basic, I guess, in comparison to the others. But it's going to be about quantum AI and quantum ML, and there is going to be a lot of redundancies with respect to things that have already been said earlier today. So I will skip over certain slides, such as this one. And I'll stay on this one for a short while because it's just beautiful pictures here. Maybe it is best for me to first demystify the two notions of artificial intelligence and machine learning. The way I see artificial intelligence is that it is automatic problem solving. Granted, that's a fairly general term, problem solving in and by itself. But artificial intelligence is the use of mathematical techniques to solve challenging cognitive problems. And an approach that has been very successfully in this direction over the last 10 years or 15 years at least, it has been around for quite some while, is the idea of machine learning. Now, what is machine learning? To demystify that, machine learning is the science of fitting mathematical models to data. Why would we want to do this? Because we can think in terms of problems as input-output systems, where we are given a certain input and would like to have a certain output. The standard example is if I give you pictures of cats and dogs, it's easy for you to classify them as this one shows a cat and this one shows a dog. We want to do that by means of machines, computers, quantum or classical. I will have to have some mathematical formulation of that problem. And the neural networks mentioned by Professor Mainzer earlier this morning are nothing but mathematical function with lots of free parameters or degrees of freedom. And the question is, can we adjust these parameters of these mathematical functions such that after some, it's called training time, they show the desired input-output behavior. So if I'll, put a picture of a cat into such a neural network, after some computation, it would say in its output layer, this is a cat. So with that said, let's talk about artificial intelligence and machine learning, more artificial intelligence than machine learning in this talk, and why people in this area, like me, are excited about the possibilities offered by quantum computers. I will mainly focus on practical applications of adiabatic quantum computing. Earlier this morning, we had many references to quantum gate computing. This is something I'll exclude from this presentation. And I wanted to point out a very close connection between a certain neurocomputing idea and the idea of adiabatic quantum computing. And the neurocomputing idea I'm referring to is the idea of Hopfield networks. Now, to the physicists in the room, you all know these Hopfield networks as Ising models, but in computer science or neurocomputing, these things are called Hopfield networks. They are a kind of neural networks, a kind of recurrent neural networks, which, let's say, consist of n neurons. Computational units I'm showing using these dots here, which are interconnected. And via these interconnections, they exchange information. And we think about the edges in this graph that shows the network as being weighted edges. The edge weights can be collected in a matrix I'll refer to as matrix W. This matrix has to have certain properties in order for certain beautiful theoretical guarantees with respect to Hopfield networks to hold. It has to be a symmetric matrix, and it has to be hollow, which means its diagonal can only contain zeros. The individual computational units in such a Hopfield network are nonlinear threshold units, which is to say they compute an inner product where Wi denotes the vector of weight values attached to that particular neuron. S is the overall state of all the other neurons in this Hopfield network. So there's an inner product between the weights of the neuron Si we are looking at and the overall state, global state of the Hopfield network. We subtract some threshold value and just compute the sign of this. So that is to say that at any point in time, all the neurons in such a Hopfield network are either in state -1 or +1. Now one can then define an energy concept for such a network. And here it is. I'll say the energy H of S of such a Hopfield network is basically a quadratic form in the state vector S. And again, you'll recognize this as an Ising energy. The interesting thing is that one can prove certain theoretical guarantees with respect to the dynamic behavior of these simple, really simple neurocomputing models. Namely that if the neurons update asynchronously, so the network is a certain state and then one neuron decides to reevaluate its own state, does so, maybe leads to a new result, flips from -1 to +1 or vice versa, or remains in the state it was. If this happens asynchronously, so one neuron at a time, then one can prove that the energy function defined for such a Hopfield network can never increase. It can only decrease. And as there's only 2 to the number of neurons possible states the network can be in, this means that we have the guarantee that such a Hopfield network will eventually settle in a stable state of locally low energy. It may not settle in the globally cheapest energy state, but it will settle at least in a local minimum. And that means that simple architectures like these can be used for problem solving. In other words, if we have this notion of the energy of such a Hopfield network, can consider the problem that is being solved here as a minimization problem, an energy minimization problem. And with respect to real-world problems, the art is then to express the real-world problem we are dealing with in terms of this mathematical formalism. However, it turns out that if you look around in the world that surrounds us, surprisingly many practically really important problems are of this form, can be expressed in terms of energy minimization problems such as this. And examples would include routing problems, planning optimal delivery routes in logistics, scheduling problems are of this form, container packing can be brought into this form. In finance, there's portfolio optimization and so on and so forth. And of course, you're all familiar with this, I hope, expression. Problems that look like this are called quadratic unconstrained binary optimization problems. And it turns out that even though this looks very innocent, it's actually notoriously difficult to solve depending on the 2 parameters W and theta of this problem. In general, minimizing expressions like that with respect to bipolar vectors is NP hard. But in order to have a look at an example as to how an Hopfield network can solve a problem, I'll go for an example that is anything but NP hard. And here is a cognitive problem. It's the K-Rooks problem. In this case, K equals 4. This problem asks for a placement of, in this case, 4 rooks on a 4x4 chessboard such that they don't threaten each other. Now, this is a cognitive problem. It requires some intelligence to be solved, but it's anything but a difficult problem. Here's a simple algorithm. We consider the first column and randomly pick a field and place a rook there. And if we know about the rules of chess, that means that in the second column, there's only 3 fields left for us to place a rook. We place it randomly in one of the fields. In the third column, there's only 2 fields left. We randomly choose one. In the last column, it's deterministic. So this is definitely not NP hard and really not a challenge for AI, but it stands in as an example for something that can be tackled using these crazily looking neurocomputing models. And I claim, without going into the details, that if we parameterize a Hopfield network using these weight matrices and threshold vectors, then the minimum energy states of a corresponding Hopfield network correspond to solutions of this 4 rooks problem. And here is an exemplary run of such a Hopfield network. I've started in a state where all the neurons were active. I can arbitrarily choose the initial state of such a Hopfield network. And then running this asynchronous update mechanism of the individual neurons. Randomly, certain neurons reevaluate their current state, and that may lead to a change in the overall state of the network. And we see that indeed, if that happens according to these rules of the Hopfield network, then the energy only goes down. It may stay constant for a couple of update steps because nothing happens, but over time it goes down and will eventually settle in a stable state from where there is no descent possible anymore. If we look at this, let's say these 4 neurons encode the first row, then it would mean no rook in the first field in the first row, no rook in the second field, no rook in the third, but place a rook in the 4th field of the first row, and correspondingly for the other rows of that chessboard. So turns out, yes, it's a simple problem, but this neural network could solve it. It produced one of the 24 possible solutions here. Now, what does that have to do with quantum computing? And again, there's a couple of slides I can easily skip because this is not a public presentation, but this is a presentation to experts in the field, so we don't have to go over the actions of quantum computing. Turns out that these adiabatic quantum computers, famously produced by D-Wave systems, are quantum devices that are tailored towards minimizing Ising energies. And from the point of view of an AI researcher, I express this as they are tailored towards solving QUBOs, quadratic unconstrained binary optimization problems. Now, this is an expression we've seen earlier. This is exactly the kind of expression that the Hopfield networks can minimize. And there is this bridge between neurocomputing and at least adiabatic quantum computing, but adiabatic and quantum gate computing are polynomially equivalent. So if a Hopfield network can do it, then a quantum computer can do it. And here is the famous recipe for adiabatic quantum computing due to Fahy and his colleagues from 2001. Again, I don't have to go through the details here. What I wanted to show you is that if we set up this Ising energy correspondingly, then an adiabatic quantum computer can solve this 4 rooks problem. And I have simulated that on a digital computer just to see how the amplitudes of all the 2 to the 16 possible basis states the quantum device can be in, superposition of all these 2 to the 16 basis states. I've plotted them individually here. And we see, yes, indeed, this adiabatic evolution of that quantum system causes with time certain basis states to be more likely in the sense that their amplitudes are growing and others to become less likely in the sense that their amplitudes are declining. And if we then in this simulated run of an adiabatic quantum computer have a look at the most likely states at the end of this evolution, we realize, yes, indeed, all of the 24 most likely states to be measured, they're at least twice as likely to be measured than any other state, encode valid solutions to this, again, very simple cognitive problem. So an adiabatic quantum computer can solve a very didactic AI problem. What's way more interesting about this is that it turns out that many of the fundamental problems we are dealing with in artificial intelligence or in machine learning are of this form, are indeed problems that can be solved by Hopfield networks and thus by quantum computers. An example is max-sum diversification, where you're given a set of data points and you want to identify k out of n data points that are as diverse as possible or maximally far apart from each other. Clustering problems can be expressed like that. Famous planning problems such as traveling salesman can be expressed like that. Important in machine learning, feature selection is a subset selection problem that can be expressed like that. Shortest path can be computed like this. The problem of training a support vector machine can be cast in this formalism. Working with graphs can be done in this formalism. Neural network training can be done in this formalism. And I'm actually sorry now that I didn't bring any slides on that. But let's have a look at, again, exemplary runs simulated with respect to this max-sum diversification problem, which is of practical importance in information retrieval, especially in web search. If you enter a query term into certain search engines, you just don't want to get all the documents that are related to that query, but you want to have a good overview of potential topics or documents related to your query. So that's done by max-sum diversification. And again, we see that if we run this on an adiabatic quantum computer, depending again on the parameterization of these problems, we get really good solutions. And the take-home message here is, in this short presentation, that what's interesting about these quantum computers from the point of view of problem solving or model fitting, that due to superpositions, we have a search process where basically every point in the search space is being considered simultaneously. And of course, there is this measurement process. So in a certain sense, the outcomes of running quantum algorithms on problems like that is probabilistic. But that is, again, nothing new to machine learners. There is many randomized algorithms in this field which have to be run several times. And you have to evaluate the outcomes of your several runs of the algorithm to indeed actually get the solution to your problem. And what's exciting about quantum computing from the point of view of problem solving in AI or model fitting in machine learning is the advantage in speed we can get. Again, without the details, you all know that if all is well, we can at least hope for quadratic speed up in search processes like that. And here is a slide I'm using for public presentations. How good is quadratic speed up when it comes to exponentially large search spaces? And this difference between exhaustive search and quantum search shows the enormous economic potential of this emerging technology. And one last slide for this short presentation is that, yes, you can run all of these things on D-wave quantum computers, but an aspect that has not been emphasized in any of the talks I've seen today is probably the question, at what costs? You can buy these machines and you can operate them. If you buy them, that puts you down a couple of $1 million. And if you operate them, that still puts you down a lot of money. Because just for cooling, these D-wave machines require more than 25 kilowatts. At this point in time, in the NISQ era, there is still this thing that it may be beneficial to, yes, think in terms of quantum algorithms, but not necessarily in terms of implementations on quantum algorithms, quantum computers. What we see here is a digital annealer, which has been produced by or developed by my colleagues here at Fraunhofer IIS. And that thing simulates what a D-Wave computer does. And it does so at less than 1.5 watts. So there is orders of magnitudes between the current generation of quantum computers and certain digital computing techniques that still can solve these kind of problems. And from the point of view of a computer scientist, what this time is calling for is quantum readiness. So we need to begin to think in terms of quantum algorithms, but as it stands at the beginning of mid-2021 right now, we don't necessarily have to worry about implementations on quantum computers. But if they become better, more reliable, and much cheaper to buy and to operate, then we are ready if we begin to think quantum right now. That was all I had for this presentation. Thank you very much for your attention.
Okay, thank you very much. It was very interesting. Yeah, so now any question from the audience? Yes, yes.
But if someone other is interested to make a remark, he should do that. Yes, thank you very much for your interesting talk. And you highlighted again the Hopfield system. And perhaps you remember, I also discussed in the last part about my talk of a Hopfield system. The difference is my approach was on the line of the quantum gates. That means it was, of course, simplified, but in principle, the squares of the Hopfield system was interpreted as quantum gates. They were that was illustrated by the Bloch spheres I used to illustrate that. And now you underlined an alternative approach, which is highly interesting. Since many years before 2019, before the quantum computers came up, namely the adiabatic quantum computing. You mentioned D-Wave and other companies which are very successful. Now, this approach in the background from a mathematical point of view is more or less thermodynamics. That means adiabatics, a Boltzmann machine in the classical neural networks approach. That means statistical neural networks. And they are more or less in the tradition of classical machine learning AI to optimization problems. So my question is, this approach, isn't it restricted to all kinds of optimization problems? That means only AI problems which can be translated into an optimization problem can be handled by the adaptive annealers.
Yes, first of all, I was actually very happy that you spent quite some time on Hopfield networks, and I was also happy that you spent time on a different point of view on Hopfield networks, like as a system of qubits, which can be in superpositions. That is indeed different to the look at Hopfield networks I had in this presentation. So that and in a sense that beautifully complements each other, because after I've seen your talk earlier this morning, I was actually sad that I need to update these slides. I have to include sort of like your point of view or vision there, because you're right. There's another way of how we can think about Hopfield networks in the day and age of emerging quantum technologies. And now to your question, yes, what I've done here is basically to show that quantum computers can help us with a certain problem class. And I am always using these kind of problems because the connection between what has been known in this area of machine learning, artificial intelligence for at least 40 to 50 years now, and quantum computing is so close. Because what these adiabatic machines are doing is they solve these kind of problems, which have been around for 50 years in AI. And that is always to show to mainly other peoples in AI that, well, if you understand these Hopfield networks, then you don't have to worry about quantum computing. Because if you understand them, then you basically now have a new tool, arguably faster tool, maybe once we get around decoherence and these kind of things. And that's the reason why I'm stressing the Hopfield networks here. Now, to your real question, is this confined to certain problems? Yes, at first sight, but at second sight, it turns out that this problem class is super large. In the end, it basically depends on the size of your Hopfield network, or the number of qubits when we're talking about an adiabatic quantum computer, as to what kind of problems you can squeeze into this formalism. And this is, right now, practically, we don't have that many qubits, so we have to stick with the usual problems. But if you wanted to, and I should actually, hopefully there is another event like that, and then I'll talk about that, you can actually express the problem of training a neural network in terms of an energy minimization problem like this. This is totally not obvious, but if you are willing to spend lots of qubits on that, then you can. And it turns out, yes, fairly restricted problem class, but depending on the size of the problem, measured in terms of states, you can do a lot of things.
Yeah, thank you.
Thank you. Thank you. As I see, there is Ferdinand Schmidt-Kahler want to ask a question.
Thank you. Actually, the question refers to this comparison which you made at the end to compare D-wave machine and a classical simulator of this process. I just want to make a statement that the D-wave machine is really not a quantum computer. Okay, it is the comparison Rainer Blatt made at the beginning. If the D-wave machine would be a quantum computer, turn this argument around, it would not be possible with this amount of qubits to simulate it such easily. So it is a mixture of thermal and coherent interactions which is going on there. And that is, of course, not what we want for the final stage. If we have the final stage, we need a coherent annealer, and people are going for this, also in superconducting, but also in Eintrap approaches, people go for a coherent annealer. And as far as I know, maybe Frank Wilhelm knows more, there is a coherent annealer research to say 10, 15 qubits possible at the moment. Then you have a different type of, and it is completely equivalent actually, whether you do a gate-based or an annealer-based approach. If you are restricting yourself to coherent annealer, okay, that is not this case here, D-wave. So thank you for making it's really, I would say it is rather not a transparency here, which we see that shows that it is so simple classically. It is rather a transparency which shows that D-wave is not producing any quantum computers at the moment.
Maybe to put this into context, it is totally not simple to do it on these machines. They are super specialized FPGAs, which can actually run several tens of millions of bit operations per second, so an extremely high amount of flops, but at very low cost. So it's anything but simple. Right? This is sort of like a self-made solution similar to what Fujitsu is selling. They are selling these digital annealers, have been all over the media lately. And maybe I need to widen this presentation. My co-workers are actually working on variational quantum approaches where if you're given a Hamiltonian, and once again, in machine learning, a lot of problems can be cast in terms of energy minimization problems. And if you have this Hamiltonian, you can basically run it on these annealers, But the question is, what kind of quantum gate sequence would you have to sort of solve the same problem? And that is where a variational approaches come into play. And I'm now regretting that I haven't mentioned this here. So there is a step on top of what I've presented here. In machine learning, you often have, surprisingly often have, these energy minimization problems. And in an additional step, you can easily implement them on these D-wave machines. But in an additional step, you can actually rewrite them in sequences of unitary operations, such that you could run this on an IBM machine, for instance.
Okay. Yeah, thank you. Thank you very much. Another question, or any other one want to ask? Okay.
Can I ask a question?
Oh, yes, Rainer. Yeah.
Thank you, Julio. I just alluded to this morning. I did not explicitly say it, but the variational stuff, that's what we use usually in our hybrid ansatz. So when you just take then, say, a quantum, an analog quantum computer as we have it, that's your analogy to the Hopfield model with the E-sync dynamics that we are using here. So we have certain number of operations with which we can just tap into the Hilbert space, and then we just measure one, but we also could measure several quantities, like several expectation values. Isn't that then the purer, the nicer work? I mean, the D-wave was the first, I agree, but it's we can fight about this. I was there, and this is not a quantum machine, and Ferry and I know that. But if you really want to use this with our 50 qubit analog simulator, and we have up to 70 to 100 qubits right now, I think that would be a real powerful thing, because we are limited at this time to about 20, maybe 25 parameters. We need a bit more insight into the classical minimization for the variational calculus to actually do this. And I think that would be an ideal way to combine things, because with 50 qubits, I'm sure we can beat much of the air out of other approaches.
Oh, I would love to have the opportunity to say, like, the algorithmically, what I've talked about is platform agnostic.
Yes.
It really doesn't matter if we do this on a D-wave machine, if we do it digitally, or if we could run it on an analog optic device. So it's actually
device, it's an analog quantum device. Optic devices are usually not quantum.
Yeah, yeah.
Let's talk about this offline. I would love to.
Yes, I would actually love to have the opportunity to run this on such a machine. If you need practical problems to demonstrate the benefits of your technology, I can give you as many practical problems as you like.
I'll call you and then we talk about this.
Awesome, awesome.
Okay.
Yeah, thank you, Julio. Thank you, Marco, for your chairs. Thanks to all speakers for their excellent and exciting talks of high competence. My impression is, yes, indeed, the quantum world, with first thought experiments of Schrödinger and Einstein, you remember this morning, has already arrived, not only in research, but in economy, in politics, and in everyday life. And that was underlined especially in the last talk. After the first generation of quantum technology with everyday electronics, we are already living in a second generation with prototypes of quantum computers, classical supercomputers with quantum simulations, quantum communication, and quantum cryptography. The talks demonstrated, I think, that we are already in the transition to a third generation of quantum technology with, for example, we heard it in especially in the talks in this afternoon, with universal quantum computers, quantum internet, and quantum artificial intelligence. Now concerning Europe, Europe is in a global competition of these key future technologies worldwide. Different countries and companies started already ambitious initiatives, and therefore I think we, as European Academy of Science and Art, and that is an internal remark to the members of our academy, we should aim at a position paper, bridging foundational research as well as applied engineering and societal impact. And I think that is well represented in our different classes.